so let's get started with today's topic. Okay, here we go. Okay, so for the person that have already participated in our webinar series, welcome back. To the ones that have not participated, welcome to our webinar series. What we're trying to do is every other time when it's available, we'll go through a topic of injection molding and trying to teach the cause and effect behaviors in injection molding. That's really what we are all about, is trying to teach the interactive behavior in injection molding. And today on the agenda is, again, we'll talk a little bit about cause and effect behaviors, a quick overview. We'll talk a little bit about the circle of knowledge training system we have designed, which is very beneficial to all parties involved, being that injection molders, part designers, mold designers, and processors. We'll go over then the actual lesson about flow restrictors, and we have a small Q&A session. So for the Q&A session, it's always a little difficult to get Q&A in. So if you have a question, please make sure you type it in the chat area, and I will see it then. And if a question comes in, then we will definitely talk about it. If you have questions that are a little bit more in depth and want to talk to me directly, you're always welcome to call or send us an email. The address and everything will be shown at the end of this presentation. Okay, so let's get started. Injection molding industry. Injection molding industry is lots of knowledge is required. Yeah, understanding complex behaviors and interactions in the molding industry is critical in order to stay competitive and ready for the future. So after 25 years of doing simulations for the injection molding industry, I've decided, well, it really is important for all of us to understand each other's business just a little bit better. The part designer needs to know a little bit more about mold design and processing, and the processor really needs to understand a mold design a little bit more in depth to make right decisions on the machine to get better part quality. So what is molded part requirements? We have molded part requirements that need to be adhered to and achieved during a molding process. And there are certain things that are important. We talked about this again. It's the critical dimensional tolerances of molded parts. That's very important to understand before you even try to design a part, design a mold, or even process a part. Very important. There also is the structural strength and requirements need to be known to the part designer to pick the right material for the molding project. The process engineer often is tasked to look at the appearance and the aesthetics of a molded parts. Do we have splay? Do we have weld lines? Do we have surface imperfections? Do we see fibers on the surface of the part? So the molder at the machine really needs to look at this very carefully and try to adjust the quality of the part by setting up the molding environment correctly. And therefore, of course, he needs to know and understand part design, mold design, and guess what? The material as well. We also need to understand what is acceptable in shrinkage and warpage. Now, what's the warpage behavior of a part? To be honest, if a process engineer at the machine sees part warpage, in general, he has very little opportunity to solve this problem. Shrinkage and warpage behavioral problems should be designed and optimized out of a part and not in the molding stage. So the part design optimization is very key before you actually build a mold and before you even process a tool. Another very important factor is the assembly functionality. Most plastic parts, they're either made with another plastic part or they're made with a metal part. If we just think about under the hood components as in molded parts, valve covers, etc., or connectors under the hood in a car, they have to withstand a lot of heat. a lot of vibration, and they usually are mounted to metal parts. So understanding the shrinkage and warpage and molded and stress behaviors in the functionality of a plastic part to a metal part is key. If that design is not optimized, the molder has at the machine no chance of really molding a structurally strong part. Yeah, it's like the old saying, garbage in, garbage out. If the design is not good, the molder and the machine can't do anything about it. Let's talk a little bit about what really our mantra is at Kruse Training is the circle of knowledge. And the circle of knowledge really is very important for us. It means that the process engineer, the part designer, and mold designer, they really, really need to work together. They need to understand each other's business to help each other to design and optimize part, to design and optimize mold, so the engineer at the machine has a much better chance of creating a robust molding window, so that he or she can actually mold a quality part. For that, we have created this online knowledge and training platform under krusetraining.com. These are very focused learning lessons. At the moment, we have 87 available, and very soon we are adding more, and we'll have a total of 96 very soon. 96 focused learning lessons. They're anywhere between 15, 20, 25 minutes, depending on how often you like to repeat certain things within a lesson. But they're very concise about a particular subject. They go right to the core of the knowledge you need to know and need to have. And we call this a knowledge system and a training tool because the knowledge system, you can really access this system like a Wikipedia type deal. Wikipedia for injection molding. You go in, you get your knowledge, you come out and continue with your job. As a learning tool, we actually have a learning management system in the background where you can really sign up certain new engineers to train on our system and actually getting certified as well. Online, everything is online, self-paced, 24/7, 365, on any device, phone, tablet, phone, computer, anywhere in the world. That makes it so amazing. The only thing you really need is a good internet connection. Okay, so let's get to the subject matter of today's lesson. We'll talk about flow restrictors. So learning about flow restrictors, we all know about flow leaders, but we also have the possibility of flow restrictors. Okay, so let's go into the lesson and we'll stop and discuss a few things about flow restrictors.
Designing parts with nominal wall thickness is ideal, yet not always possible. In the previous lesson, you learned that flow leaders, or internal runners, can be used as a design feature to achieve uniform filling and packing. In this lesson, we will introduce flow restrictors, another design feature that serves a similar purpose. In this lesson, you will learn that flow restrictors can be used to redirect and restrain material flow and achieve uniform filling patterns, can avoid air entrapment issues, influence flow hesitation, and racetrack effects. Flow restrictors may be used to redirect material flow by repositioning weld lines so they are in non-critical areas. Adding flow restrictors can eliminate racetrack or backfill conditions, which could lead to air trapping. A few other points to consider regarding flow restrictors are: flow restrictors may be designed into a family mold runner system. A small runner segment is considered a flow restrictor. Flow restrictors can have varying lengths and thicknesses throughout a part. Flow restrictors can slow down a flow front advancement to achieve a uniform fill.
So very important to understand these little subject matters, flow restrictors. And if you have a very complex part design with varying wall thicknesses, you inherently have in your design flow restrictors and flow leaders. Yeah, some wall thicknesses are a little bit thicker, and they act as a flow leader. Always remember, plastic flows the path of least resistance. So the material goes wherever it's easy. It's like us. We are, going through the door and not through the wall. So it's easier to go through an open door. So the plastic likes the same behavior. And again, every complex part design has inherently incorporated flow restrictors and flow leaders. Okay.
There are potential downsides to using flow restrictors in part design. For example, the restriction of cavity pressurization can lead to a structural weakness and a different surface appearance in thinner sections. In this lesson, we will show how flow restrictors can eliminate an air entrapment condition on a cover part, and then show how to optimize the flow pattern in a structural grill part.
Very simple geometries, okay? Because if you understand the principle of a flow restrictor or a flow leader, you can adapt this principle to any kind of complex part design. But it's always very important to understand it on a simple part before you try to attempt this in a complex part. Okay, one more thing. This part here on the left, that's our first part. And what this is basically a cover for a filter housing, for example, for a pool filter. And the objective here is that the designer has designed this part, and there should not supposed to be any marks on this surface, round surface in the center. So we cannot really place a gate there. And the part needs to be clear, and we have a so-called see-through tolerance. So we need to be able to look through this filter cover to really determine what's underneath. How is the water flowing? What's the consistency of the pool water? Is it stained or whatever? So that's the real mantra with this particular part. The internal surface is really important for the function of the part. Let's take a look.
Let's start with the sample cover part, with a center wall thickness of 2.5 millimeters and a rim thickness of 3.5 millimeters, which is structurally strong enough to achieve a proper sealing condition in this assembly. Due to fluid flow observation requirements for the part's function, the gate cannot be placed on the center portion of the part. The flow pattern of the filling indicates that part fills without any hesitation or entrapment issues. But for the purposes of this example, we have determined that on inspection, the see-through requirement of the part is not sufficient, so the center thickness needs to be reduced. By increasing the clarity of the cover, the fluid flow underneath will be more visible. To accommodate the desired clarity capabilities, the center thickness is reduced to 1.75 millimeters, with all other variables remaining the same.
As you can imagine, wow, 1.75 millimeters. The rim is 3.5 millimeters. We have these holes in here for the screws. Underneath the cover, this section here needs to hold the seal, so that needs to be very flat. But, we need this thin wall to be able to look through.
Looking at the filling pattern for the revised part design, you can see that there is a hesitation and racetrack effect, creating air entrapment in the part near the end of fill. So although the reduction in wall thickness achieved the desired clarity, it also created an air entrapment issue. We will now add flow restrictors to this design to achieve a uniform fill pattern. The center wall will remain at 1.75 millimeters, and the rim will be 3.5 millimeters around the screw holes, allowing for proper sealing. The new part design includes restrictors between the screw holes as shown on screen.
Yeah, that's important. So if you are a little bit innovative and the part design can be changed that way, you still have a very thick wall here to really hold up the strength for the screw. The cutouts are on the top surface, not on the bottom surface where the seal is, so everything should be fine. So making these flow restrictors designed into the part will help us.
The fill pattern for the new design shows the material hesitating as it flows through the restrictors, giving the center portion time to flow across the part. Since we kept the screw hole areas at 3.5 millimeters, and the restrictors are designed on the outside, there is no disturbance to the sealing surface inside the part. As you can see from these examples, adding flow restrictors to the part design allowed us to achieve the desired clarity of the cover without any filling issues.
Simple part, huge problem, and solved with an easy fix. Flow restrictors on the outside cover.
Moving on to the second part design evaluation. Here you see a grill-type part that will be used as a safety cover. The goal is to achieve a uniform fill pattern across the part, resulting in more uniform pressure distribution and stronger weld lines. Keeping tooling cost in mind, we will start with a single center fan gate. The fill pattern with a single center fan gate indicates that the rib structure in the center region races ahead and the corners of the part are the last to fill. This could be an issue depending on the material that is used for the part. For example, if the material is fiber filled, the fiber orientation near the gate and away from the gate will be quite different and can result in mechanical strength variations and part warpage.
Now we all know, if this cover is is over a, let's say, a safety hole or whatever, we have here some mounting holes to put this grill over some safety area. So if the material is fiber filled and you have to have certain strength, the fiber orientation in this side versus that side through the fill pattern and through the ribs is really different. And as you know, fiber-filled materials, they shrink differently in the direction of flow versus perpendicular to the flow. So you're ending up with a very complex 3D fiber orientation challenge in this very simple grid part, which then can cause shrinkage differences and warpage potential.
Let's analyze the results using two fan gates on the same side of the part. Here you can see the original part design with a 4 millimeter rib structure and a dual fan gate setup. A disadvantage to using a dual gate setup is that it will require a hot runner system, which will result in a higher tooling cost.
Yeah, hot runner, of course, it's just a little two fan gates. We have to get the material to these gates. We could have a sprue in the middle, cold sprue, with a runner leg to each side. That's possible as well, but it will add to the flow length of the material. And if the pressures are already high, this could hinder the capabilities on the machine. So that's why it's more likely to have a dual hot runner system with a dual fan gate than just have a cold runner system that will add to pressure drop. Okay, that's what the system means.
The end of fill for the dual gate setup indicates a relatively uniform fill pattern. The pressure drop, fiber orientation, and strength requirements are most likely acceptable.
Yeah, it looks pretty good.
Let's look at another design scenario for this part. We will adjust the rib thickness for the ribs running the width of the part in the Z direction to 3 millimeters. The outside ribs will stay at 4 millimeters, and we will again analyze the results with a single center fan gate.
So all of these ribs going across are now 3 millimeters, all of them, and the outside rib thickness stays at 4 millimeters. Okay.
You can see that in this example, the fill pattern is more even than it was with the original 4 millimeter rib example. The 3 millimeter ribs in the Z direction slow down the fill in the center section, and the pattern appears more even at the end of fill.
Yeah, it's pretty even, but not quite yet.
Let's look at the same 3 millimeter rib part design with a dual fan gate setup. The fill pattern for the 3 millimeter rib structure and dual fan gate setup indicates that the center rib structure fills relatively evenly through the center, but the flow is racing around the edges of the part. This racetrack effect is a result of the 4 millimeter thickness of the outside ribs.
Yeah, racing around.
So far, we have seen 4 options for achieving a uniform fill pattern in this grill part. Now let's look at how adding flow restrictors in the form of wall thickness indentations affects the results. The image on the screen indicates the ribs in the Z direction have small cutouts that will further restrict the flow of the material through the ribs. The cutouts are staggered along the ribs, and there are more of them closer to the gate.
It's hard to see for you on screen, but these cutouts are little cutouts in these ribs in between the longitudinal ribs. We have little cutouts here all along. Most of them are closer to the center ribs, to these vertical center ribs here, and less of them when we go further out. These ribs, the 3 outer ones on each side, don't have any cutouts. Just in the center ribs, they have some cutouts, and not all the way through, just closer to the gate. So with this type of technique, can we get a more uniform fill?
The fill pattern for this example is quite uniform, and the material reaches the opposite side of the gate at the same time. These 5 examples clearly indicate that adding flow restrictors to a part design can be a good option for optimizing part design while managing tooling costs. This concludes Section 3, Lesson 3, Flow Restrictors. In this lesson, you learned that flow restrictors can be used to redirect material flow and achieve uniform filling patterns, can avoid air entrapment issues, influence flow hesitation and racetrack effects. In conclusion, the examples in this lesson show that by adjusting wall thicknesses and adding flow restrictors to a part design, flow patterns can be adjusted to achieve desired fill patterns. An important difference between flow leaders and flow restrictors is that flow leaders always start at the gate for proper processing, while flow restrictors do not. As we've seen, both options can be used to design and mold high-quality parts.
Okay, just so recap, flow leaders. This is a part from the previous lesson that I have not showed you here in this webinar series. But again, flow leaders starting at the gate and going to the outside to really promote flow. That's usually how that works. And the reason for that is, at the gate, we need to be able to pack these flow leaders out at the end. That's why they start at the gate. If you have flow leaders away from the gate, that would mean a thin section, a thick section, a thin section. So, that is really not what you're supposed to do. That's why flow leaders are actually starting at the gate, and flow restrictors can be designed into the part. So here we have a question from Alex. How do you account for the fill speed affecting how the flow restrictors affect the flow? So basically, do fill speeds really affect the fill behavior even with the restrictors? And the answer is absolutely. Yeah, and this is very key. Depending on the material viscosity, flow restrictors can have a huge impact or a small impact. The fill speed, therefore, could have a huge impact or a small impact. But if you really think about viscosities and viscosity curves, as faster you inject, as lower the viscosity will be. However, if you're familiar with viscosity curves and temperature curves, viscosity and temperature curves, this viscosity does change, but not in extreme measures. Yeah, and that's why it's important to really analyze the polymer material you are using to see the effect of fill speed on the ability to use flow restrictors. This is really important. That's exactly why we do what we do. That a part designers who work with flow restrictors really need to understand the material and not just part design. Okay, that's why the circle of knowledge is so important to understand. Okay. Okay, so again, circle of knowledge, that's why we have designed our training system and knowledge system, because we believe that the part designer, the mold designer, and the processor all will benefit from understanding injection molding in its entirety, not just their general job function. No, it is important to really understand all of it to be successful in your job. Okay, so again, this concludes the webinar for the flow restrictors. If you have any questions, please remember you can always contact me via email or phone. Thank you very much for participating, and check our website and LinkedIn for the next set of webinars that are coming up relatively soon. Again, thank you very much, and I wish you a good day.